Hi, I'm Richard Eckman from NASA headquarters. I'm the program scientist for SAGE 3 on ISS. That's the Stratospheric Aerosol and Gas Experiment aboard the International Space Station. SAGE is in fact the fourth in a series of instruments that have flown by NASA since 1979, measuring ozone, aerosols, and other chemical constituents in the stratosphere. It's provided a very long time series of observations of critical elements of atmospheric composition in the stratosphere. SAGE 3 was launched in February of 2017 aboard a SpaceX Falcon 9 rocket and was installed on the International Space Station using the Canadian robotic arm. Here in this photograph, you can see obviously an astronaut doing an unrelated EVA activity, but in the background you can see the SAGE Observatory just to the left of the solar panel. The expanded box in the lower left corner of the screen, you can see an animation of a protective cover opening and closing. This protects the SAGE Observatory from contamination in the event of particles from, for example, rendezvousing spacecraft that periodically come to the space station. SAGE 3's primary mission is to monitor ozone in the Earth's stratosphere. That's a layer of the atmosphere that starts about 16 kilometers above the surface of the Earth. Ozone is critical to shielding the Earth from harmful UV radiation from the sun, and this really is vitally important for life as we know it to exist. In the 1980s, atmospheric scientists were very surprised to find ozone behaving very unexpectedly in the Antarctic region during its springtime, and seasons are reversed in the southern hemisphere, so that was in September or October. And scientists found that large amounts of ozone in the stratosphere were missing for many months, and the cause wasn't immediately known. After intensive investigation, scientists found that the link of the Antarctic ozone hole was due to increases in man-made chemicals that reach the Earth's stratosphere over time. These are principally the fluorocarbons that we have used for many decades in air conditioning and refrigeration applications. As a result of all of this, the Montreal Protocol was signed in 1987, a major United Nations treaty that phased out these harmful chlorofluorocarbons and replaced them with more ozone-friendly compounds. Now, since then, NASA and NOAA have been tasked by the U.S. government to monitor ozone on an ongoing basis to look for the recovery in ozone as a result of these depletions in the Antarctic region and beyond. And you can see in the lower plot here a long time series from the late 70s onwards into the early part of this century, showing SAGE ozone trends and the leveling off of ozone as these chlorofluorocarbons were eliminated. But that's not actually what I want to talk principally about today. I want to talk about the A in SAGE, aerosols, which is another important atmospheric constituent that is measured by the SAGE instrument. Aerosols are tiny particulates in the atmosphere that come from a variety of natural and human activities. For example, they can come from dust from deserts that are blown by the wind, or from explosive eruptions of volcanoes, like this picture of Mount Pinatubo that erupted in 1991 in the Philippines. These explosive eruptions can inject aerosol particles well into the stratosphere, where they can affect the chemical composition of the atmosphere, participating in reactions, or they can affect the thermal balance of the atmosphere. In addition, aerosols can be injected into the atmosphere by fires, wildfires like those that we've had in recent years, both in the United States, in Australia, and elsewhere around the world. Last year in June, the Rykoki volcano, just northeast of Japan in the Kuril Islands, erupted in June. Here on the left, you can see a photograph from someone on the International Space Station looking down and seeing this enormous eruption. Another view of that eruption can be seen in the upper right of this slide. Here, what's interesting is to look at the transport of that plume by prevailing winds in the troposphere and higher up in the stratosphere that are moving the ash and the sulfuric acid particles from the eruption away from the immediate location of the volcano. The volcanic eruption led to worldwide effects. Even in the United States, we saw enhanced sunsets as a result of these aerosols in the stratosphere. You can see these reddish sunsets as noted in the lower right picture on the screen. The SAGE 3 instrument aboard ISS was also able to see the Rykoki eruption. Around 3 weeks before the eruption, in the upper left view, you can see typical levels of aerosols in the upper troposphere. That's 10 to 12 kilometers above the Earth's surface. The x-axis is the longitude going around the Earth. SAGE first noticed the increased aerosol from Rykoki very shortly after eruption on June 28th, around 38 degrees north. You can see that enhancement around 16 kilometers above the Earth's surface. A few weeks later, you start seeing more aerosols in the lower stratosphere, around 16 kilometers above the surface of the Earth. And a full 5 weeks later, the global impact from Rykoki is well seen by SAGE, showing enhanced levels of aerosols well into the stratosphere as high as 18 kilometers above the Earth's surface. Wildfires, which have become increasingly prevalent in recent years, are another source of atmospheric aerosols. This is a pyrocumulus cloud taken aboard an aircraft about a year and a half ago in the western United States, showing a cumulonimbus, a thunder cloud produced by the wildfires. This enables the transport of aerosols into the upper troposphere and onwards into the stratosphere. In addition to the Australian wildfires last year, SAGE 3 also was able to monitor impacts from the California wildfires from last September. In the lower left column, we see a vertical profile of aerosols from near the tropopause, about 15 kilometers above the Earth's surface, all the way to 30 kilometers, well into the stratosphere. You can see that profiles seen in mid-September from SAGE are very much elevated compared to normal background levels of aerosols. And these came from the California wildfires and demonstrate their global impact. In summary, SAGE will continue monitoring aerosols, both natural background levels, but also from future eruptions and from future forest and wildfires. Thanks for your attention.